So let us see the star delta starting. So before going to star delta starting, we must know the property of our star and a delta connection. Okay, here you can see in star connection, okay, if I apply line voltage V, okay, between two lines, the phase voltage will become, if my line voltage is VL, this is my line voltage, okay, the phase voltage will become, phase voltage means the voltage between one phase, one single line and a neutral point. This is my neutral point in star, okay. So the phase voltage will be between one line to neutral point, that will become line voltage by root 3, okay. This is the voltage expression for phase voltage in star connection. So let us see the currents. Here we have two types of currents, line current and phase currents. Because it is star connected, here you can see the line is continuous throughout the phase, that means the line current and phase currents are equal because it is a series connection. So line current and phase currents are equal for star. This is for star connection, okay. Let us see the delta connection properties. Here this is delta connection, okay. Here you can see our line voltage equal to phase voltage. The line voltage between two lines is equal to phase voltage, okay. This is the voltage across this phase, this is equal to phase voltage, which is also equal to line voltage. That means the property of delta is line voltage equal to phase voltage. Now let us see what is happening to the currents. Here my line current is coming like this and it is splitting into two directions, okay. That means my line current is equal to root 3 times my phase current in delta connection. So these are the properties of our star and delta connections we must know to understand the star delta connection, star delta starting, okay. So let us see the star delta starting. So as I earlier told you that the star delta starting is used for squirrel cage induction motors, stator connected in delta. That means delta connected stators of squirrel cage induction motors will be operated using star delta connection, star delta starting, because it is the stator of our induction machine can be connected in star or delta, but irrespective of our stator, rotor will be in star for slip ring induction motor. That means stator can be star or delta, okay. So auto transformer starting can be used for star or delta connected stator, okay, but our and D valve can also be used for star or delta connected stator, but our star delta starter used for delta connected stators, okay. Our delta connected stators of squirrel cage induction motors will be started using star delta starters, okay. Now let us see the construction of star delta starter. Here we will be having a two-way switch. Here this is my two-way switch, okay, which can be turned on to star in starting condition and delta in the running condition, that I am going to explain. So let us see the star delta starting. So this is my star delta starting diagram, okay. So let us see. So this is my stator of our squirrel cage induction motor and this is the rotor, okay. As I earlier told you, this is delta connected stator, okay. So now this is our three-phase AC supply. We are going to supply the stator using three-phase AC supply, but here you can see the terminals, the stator terminals are having, I told you about the stator terminal box. Here there will be three terminals, U1, V1, W1, and here W2, V2, U2, okay. So the stator terminals will be supplied using three-phase supply, okay. This will be go into our stator winding and this will come to this winding will be come out like this, okay. So this, if you connect these 3 points to using one bar, okay, this will be star connected stator winding, or if you connect this like this will be delta connected stator winding. I earlier told you about the stator connection, okay. The winding of the stator can be connected in star or delta using our terminal box. Here if you want to use a star connected stator, okay, you have to short circuit these 3 terminals. This will be my star connected stator. If you want to get a delta connected stator, you have to short circuit these 3. This will be my delta connected stator of our induction motor, okay. So based on the terminals short circuiting, we can make the stator winding in star or delta, okay. So that is the idea here. You can connect the stator using the terminal box either in star or delta, okay. So here we are using that concept. So at the time of running, we are going to make the stator of our induction motor as star connected circuit, and under running condition we are going to make it to run as delta connected stator winding. So that is the idea. So here we have a two-way switch. Here this is our two-way switch. Okay, here at the time of starting, this two-way switch is connected to down position. Here you can see, that means whenever it is down, turn on to down position, you see these three terminals are short circuited. That means our stator winding will be star connected one at the time of starting. Okay, at the time of starting, we are going to make the two-way switch to turn on to our short circuit terminals of stator winding, that will make the stator winding into star connection. Okay, under running condition, we are going to move this two-way switch to upward position. Okay, that will be, okay, this will be connected to this. Okay, this will be connected to this under running condition. You can see the winding is now connected in delta. Okay, this is delta. Here you have short circuited like this. Okay, so under running condition, our stator winding is delta. So under running condition, under starting condition. So for starting, we are using the stator winding as delta, and under running condition, we are making the stator winding under as delta. Okay, so for starting it is star, for running it is delta. So this is the idea. So how can we reduce the starting current using this star delta concept? Okay, let us see. So we are going to see the star here and delta here. This is my line voltage. Okay, this is my line voltage V. So what will happen to phase voltage? Phase voltage will be V by root 3. Okay, this is my phase voltage, and line voltage of star connection I am naming this ILS, which is equal to my phase voltage I phase S. Okay, now what is happening to the line voltage of our delta connection, which is equal to phase voltage? Okay, but what happens to line voltage if it is my impedance Z? Okay, the phase voltage, the phase current is like this, short circuit current ISC. So the line voltage will become root 3 times my ISC, or root 3 times my phase current. Okay, so let us see, this is my line current of delta connection. Okay, so now let us see the phase voltage and line voltage here. So the line voltage equal to root 3 times phase voltage here, but line voltage, line current is ILS is equal to my phase current in star connection. Okay, here my line voltage is equal to phase voltage, but my line current is equal to root 3 times my phase current. Okay, this is, I am representing it as ISC. Okay, so this is the concept. Now let us so under starting condition, our two-way switch will be turned on to this star connection. Okay, so then our stator winding will become star connected winding. Okay, so after some time, whenever our motor attains some speed, this two-way switch will be turned on to our delta connection. So our stator winding will become delta winding. So our at the time of starting, our stator winding is connected in star connection, and at the time of running, our stator winding is connected in delta connection. So this is why the name, it says star to delta starting. Okay, initially it is starting and starting condition, and on a running condition it is delta. So now let us see the behavior of currents here, so that we can obtain the star relation. So here the voltage across line to line is root 3 times phase, or phase voltage is line voltage by root 3 in case of star. Okay, because it is a series connection, the line current and phase currents are same. Okay, so let us see the under delta connection. Here the line voltage and phase voltage are same in delta connection, and the line current is root 3 times phase current, or phase current is 1 by root 3 times line current. Okay, so now let us see the currents, phase currents in each and every winding. Here the phase current will be I phase star, I am representing it as I phase S. Okay, that will be V phase V by root 3 by impedance of our stator winding. So this will become V by root 3 times my stator impedance. Okay, so what will be the line current of star connection? That will be equal to phase current, that is I phase star connection, which is equal to V by root 3 times Z. So I am making it as equation 1. So now let us see the behavior of line current in the delta connection. So what is the phase current here? The phase current is phase voltage, which is equal to line voltage. Okay, phase voltage by our stator impedance. So what happens to the line current? That will be equal to root 3 times my phase current. Okay, root 3 times my phase current, that will be equal to root 3 times what is the phase current here, VL by Z. So if I have to divide my line current in star and line current in delta, that will become, let me divide the line current in star and line current in delta. So that will give V by root 3 times Z by root 3 times V by Z. Okay, I can cancel out V by Z. So the left will be 1 by 3. Okay, that means the starting current, the current in star will be equal to 1 by 3 times current in delta. Okay, so this is the idea here. You can see at the time of starting we are making the stator winding equal to star connection. Okay, that is the line current in the star is equal to 1 by 3 times of whenever our machine is running at delta connection. If there is no star delta starting, our stator winding is in delta connection. So if I have a 30 amps under delta connection without any star delta starter, so if I have the starting current as 30 amps, this is my starting current. Okay, so what will become if I add star delta starter? That will become 1 by 3 times my current in delta. This is my current in delta. So the star connected stator will consume 1 by 3 times 30 amps, that will be 10 amps. So before star connection, under starting condition without any starting method, the stator of squirrel cage induction motor drawing 30 amps of starting current. So whenever we are added star delta starter, at the time of starting, our starting current drawing from the supply will become 1 by 3 times our starting current drawing whenever the stator is connected in delta. That means 1 by 3 times 30, that will be 10 amps. So the starting current is reduced by 1 by 3 times. Okay, our starting current in delta is reduced by starting current in star reduced by 1 by 3 times starting currents of delta. So this is how we can reduce the starting currents using star delta starter. Okay, now let us see the relation between torques. Okay, so we have the expression, that is my star connection line current in star equal to 1 by 3 times line current in delta. So when I shift this to phase currents, so the phase current in star will be equal to 1 by 3 times. What is the phase current here? So what will be the phase current? Phase current will be here my line current ILD equal to root 3 times my phase current. Okay, so this is the relation for delta. So I am replacing my ILD with root 3 times my phase current in delta. Okay, this is my delta. So that will become the phase current in star equal to, this will be equal to 1 by root 3 times my phase current in delta. This is nothing but short circuit current. So this is the relation. The phase current, line current is reducing by 1 by 3 times. Okay, but the phase current is reducing by 1 by root 3 times. Okay, so now let us see the relation between starting torque and full load torque. Okay, here I phase and ISC are phase currents. Okay, phase currents. Here these are line currents. Okay, you know the difference between line currents and phase current, I think. Okay, now let us see the starting torque and full load torque. Here at the time of starting, that torque is proportional to IST whole square by S. Starting at the starting, S equal to 1. Okay, I can replace the S. So at the time of full load running condition, the full load torque will become IFL whole square by SFL. Okay, now what is the starting current? Starting phase current here, this is nothing but my star connection phasor current. Okay, because it is at the time of starting, the type of winding is star connection. So that star connected phasor current is equal to, that is my IST equal to I phasor under starting or star connection, which equal to 1 by root 3 times my I phasor under delta connection. Okay, so now let us see the relation between starting torque and full load torque. That will become, I am replacing IST with 1 by root 3. So let me write IST by IFL whole square into SFL. Okay, that will, I am replacing IST with 1 by root 3 times phase current in delta. So that the expression for starting torque to full load torque in star delta transformer will become, star delta starting will become I phase delta by IFL whole square into SFL. So the whole expression will become TST starting torque to full load torque in the star delta connection starting will be equal to 1 by 3 times ISC by my IFL whole square into SFL. I can write the IPH phase in delta equal to my short circuit current. Okay, so this is the expression for star delta starting. Okay, we have obtained 4 expressions. one is DOL starting, okay, one is for DOL starting, another is primary resistors, another is auto transformer, and this is star delta. Okay, we need to remember all these expressions. I am going to write it in the next slide so that you can understand it better. So on the star delta starting, we can reduce the whole fraction into 1 by 3 times. Okay, you can see here in auto transformer starting we got k square as the fraction. Okay, so I can say that star delta connection is nothing but a auto transformer starting with percentage tapping equal to 1 by root 3. Can I write like this? If you replace k square equal to 1 by root 3 whole square, so this will become my 1 by 3. So I can say it as our star delta starting is nothing but a auto transformer starting with the tapping percentage as 1 by root 3. Okay, so this is the idea. Let me write all the expressions once so that you can remember. So here you can see the starting torque to full load torque relations for DOL starter, primary resistor starter, auto transformer starter, and star delta starter. You can see the difference. Okay, for DOL starter it is ISC by IFL whole square into SFL. Here ISC is nothing but short circuit current at the time of starting, which is nothing but inrush current. Okay, because there will be no back EMF at the time of starting, so our ISC will be in the order of 5 to 7 times of our full load current. Okay, so this is the idea. So DOL is TST by TFL into ISC by IFL whole square into SFL. So the primary resistors starting will be TST by TFL into X square. X is the fraction of voltage that we are going to apply for stator winding. So ISC by IFL whole square into SFL. At the time of auto transformer, here K is nothing but percentage tapping of auto transformer. So K is percentage tapping here, and for star delta starting, the ratio between starting torque to full load torque is 1 by 3 times ISC whole by ISFL whole square by SFL. Okay, so this is about starting torque to full load torque ratios of our starting methods. Okay, so here you can see that this ratio ISC by IFL whole square into SFL is a ratio for DOL. So you can replace each and every one. Okay, so my starting torque, the torque in primary resistors starting method equal to X square times our torque in DOL method. So similarly our starting torque in auto transformer method equal to K square times torque in DOL. Okay, and finally our starting torque in star delta can be equal to 1 by 3 times our torque when the machine is operated under DOL condition. So these are the important expressions to be remembered. You will be asking questions based on this. Okay, and you can see the line current in star is equal to 1 by 3 times line current in delta. Okay, in star delta connection. Okay, and here the primary supply line current, that is my starting current, equal to my K times K square times my ISC in auto transformer starting. Okay, this is my supply line current. IST is nothing but my supply line current equal to K square times ISC. So these are the things to remember. Okay, next class we are going to do some problems on these expressions so that you can understand the starting methods clearly. Okay, we are left with one more concept, that is slip ring induction motors starting method, which is rotor restart method. Okay, with that we are going to conclude the starting methods of our 3-phase induction motor. Okay, thank you. So let us do some problems for starting methods. Okay, here I have considered a problem based on auto transformer starting. Let us see the problem. The problem is determine the suitable auto transformer ratio. Suitable auto transformer ratio is nothing but percentage tapping, which is nothing but K. For a starting of 3-phase induction motor with line current not exceeding 3 times full load current. Okay, then the short circuit current is 5 times the full load current and full load slip is 5%, and you have to estimate the starting torque to full load torque ratio. So let us write the given data. First, given data is saying that we have to find out what is to be found. To be found is our K value and TST by TFL ratio. So these are the things to be found. Okay, now let us write down the given data. He has given that line current not exceeding 3 times the full load current. So line current is nothing but our starting current, which should be equal to 3 times our full load current. So that is my full load current is IF. Okay, here this is my line current, this is my supply line current. Okay, this is my full load current. Okay, so now the short circuit current is 5 times the full load current. That means my ISC short circuit current is 5 times the full load current. Okay, the ISC by IFL ratio will become 5. Okay, now we have to find out the ratio of transformer and TST by TFL. So for auto transformer starting, we have a relation between our supply line current and short circuit current, that is our supply line current, which is nothing but starting current, equal to K square times our short circuit current. So this is the relation for auto transformer starting. Okay, this is my supply line current, this is my short circuit current. Okay, this is my supply line current, this is my short circuit current. Okay, now let us substitute the values. Here our IST is nothing but 3 times our full load current, which equal to K square times our ISC is 5 times my full load current. Okay, so you can cancel out IFL here. Okay, so the left thing is K square equal to 3 by 5. So the value of K will be equal to, what is the value of K here? It is 0.6. Sorry, 0.6 volts on a root, that means K equal to root 0.6, that will become 0.775. So percentage tapping is 77.5%. Now let us see the relation between starting torque to full load torque. So in case of auto transformer, okay, we have known the percentage tapping. So I can write the relation between starting torque to full load torque equal to K square times ISC by IFL whole square into SFL. So this is the relation for auto transformer starting. Okay, now let us see the value of TST by TFL. TST by TFL will become K square is nothing but 0.6 here. Okay, 0.6. My ISC by IFL ratio is 5 given in the question. Okay, that is 5 square, and slip rate full load torque is 5%. Here I forgot to mention it. SFL is nothing but 0.05. Okay, so you can substitute the value of our full load slip. So the ratio will be equal to 75. 0.75, which equal to 75%. So our starting torque in this question is equal to 75% of our full load torque. So this is the idea. So using these expressions, so these two are the important expressions to be remembered in auto transformer starting. Okay, our starting torque, which is nothing but supply line current, okay, supply line current equal to K square times our short circuit current. So this is the thing for auto transformer starting. We will be doing another problem based on this auto transformer starting. Okay, let us take another problem for better understanding. So let us see another problem on auto transformer starting. The problem is the full load slip of a 400 volts 3-phase cage rotor is 3.5%. That is the full load slip is SFL. Okay, and with locked rotor. Okay, here with the locked rotor, the full load current is circulated when 92 volts is applied between the lines. Okay, actually the given line voltage is 400. Okay, but he applied 92 volts only to get the full load current under locked rotor condition. Okay, then find the necessary tapping on auto transformer to limit the starting current. So because it is saying limit the starting current, we can consider it as auto transformer starting. Okay, the question is regarding auto transformer starting. Okay, because he is asking to find the necessary tapping is nothing but K, percentage K, and to limit the starting current, that means it is, the question is regarding auto transformer starting. Okay, so the starting current, we have to find the percentage K of auto transformer to limit the starting current to twice the value of full load current. That means my IST is equal to twice the full load current. IST is nothing but, IST should be equal to twice the full load current. It should not exceed beyond 2 times the full load current. Okay, so this is IST equal to 2 times the full load current. So then also find TST by TFL ratio. So we have to find out the K first. So for that we have for auto transformer we have a relation between starting current to full load current is K square times IFL. Okay, so our starting current is 2 times full load current. Okay, 2 times my full load current into K is equal to K square into IFL. Here the IFL is find out under locked rotor condition, it 92 volts between the line to line. Okay, so but the actual rated voltage is 400 volts. So the full load current will be calculated based on the full load voltage only. Okay, for 92 volts it is IFL. So we have to find out for full voltage rating, that is we have to find out for full voltage, that is equal to 400 by 92 times IFL. That is under at rated voltage. At rated voltage, the short circuit current is 400 by 92 into IFL. This is under rated condition. So the full load current will be equal to 400 by, this is actual ISC, right? ISC square times ISC, 400 by 92 times IFL. It is at rated voltage condition. So you can find out the full load, you can find out the K value here. Okay, K square equal to, what is the value? K square equal to 0.46, but K equal to 0.678, that equal to 67.8% of 67.8% of tapping is required to limit the starting current to twice the full load current. So in order to limit the starting current to 2 times the full load current only, we have to make the tapping on auto transformer equal to 67 times 67.8%. Okay, now let us find the second question, that is TST by TFL ratio. For auto transformer, the ratio is equal to K square times ISC by IFL whole square into SFL. Okay, so the ratio will become 0.678 whole square into ISC by IFL. ISC by IFL ratio is ISC by IFL equal to 400 by 92. The ratio between ISC and IFL is 400 by 92 here. So the value of TST by TFL will become, what is the value? The value of TST by TFL will become 0.304. That means 30.4% of full load. The starting torque is 30.4% of full load torque. So this is based on auto transformer. Okay. Now let us take a problem on star delta starter. Okay. So this is another problem. Here you have to solve for 2 starting methods. Okay, let us see that. Determine the TST by TFL ratio for a star delta starting and auto transformer starting with 70.7% of tapping and the short circuit current of the motor under normal voltage condition, that means under rated voltage condition. In previous problem we have done it was given at 92 volts the IFL. Okay, we found out it is at a rated voltage condition. Okay, that is rated voltage by given voltage into IFL. Okay, so he has given under rated voltage condition the short circuit current is 6 times the full load current. Okay, so we have to find out the short circuit current under rated voltage condition only. Okay, whatever the voltage mentioned in the problem, we have to find out the short circuit current under rated voltage condition only. So under rated voltage condition, our short circuit current is 6 times the full load current and the full load slip is 4%. Then neglect the magnetizing current. Why did he mention to neglect the magnetizing currents? Because our transformer need to be supplied some core component, so that is called a magnetizing component. We have to neglect for doing problems here. Okay, now let us see the given data first. So given data is percentage tapping, which is nothing but 70.7%, that is root 2. Okay, sorry, 1 by root 2. Okay, this is percentage tapping. The short circuit current of the motor under normal condition ISC equal to 6 times my IFL. This is another given data, and slip at full load condition is 0.04%. Okay, then what to be find? To be find we have to find out our TST by TFL ratio at star delta starting, another is auto transformer starting. Okay, we have to find out the TST by TFL ratio for 2 types of starting methods here. So I am going to consider first one, star delta starting. Okay, the relation between starting torque to full load torque for star delta starting is equal to 1 by 3 times ISC by IFL whole square into SFL. So with this expression, the problem is done for star delta starting. So you have to remember this expression. That is the only thing. Okay, so substitute the values here. So that will become 1 by 3 times ISC by IFL equal to 6 here. Okay, 6 into our full load slip is 0.04. Okay, so what will be the value for our star delta starting? That will be equal to 0.48, which is nothing but 48% of full load torque. That means the starting torque of our star delta starting is 48% of full load torque. Okay, so now let us do for auto transformer starting. So the expression for starting torque to full load torque is K square times ISC by IFL whole square into SFL. Okay, this is the expression for starting torque to full load torque ratio for auto transformer. This was for star delta. So now substitute the values. So K is mentioned as 1 by root 2, so I am squaring it. So the ratio between starting torque to short circuit current to full load current is 6. Okay, and the full load slip is 0.04. So that will become, okay, 0.72, which is nothing but 72%. Okay, with 1 by root 2, 70.7% of tapping, we can obtain our starting torque in auto transformer starting equal to 72% of full load torque. Okay, earlier the starting torque in our star delta starter is 48% of full load torque, but in auto transformer starting you can see it is improved up to 72% of full load. So we have the chance to vary the starting torque with variation in our K value in auto transformer starting. So this is about auto transformer and star delta connection. Okay, so with this I am concluding auto transformer and star delta starting. In the next class we will be dealing with starting method of slip ring induction motor, that is rotor wave start method. Okay, thank you.